So, my lecture is on sparse modeling and the connection this has to deep learning. More specifically, my lecture is about a proposed theory for deep learning based on sparsity. So let me give a context for that. You are all familiar with the amazing success that deep learning has. This conference is a manifestation of this success. Now, the thing is, the knowledge that we have today in deep learning is mostly, perhaps all of it, empirical. The algorithms, the tricks, the architectures, they are all empirical. They are all found by trial and error. And a theory is very much missing, a theory that will explain why this works the way it works, which architectures are performing better than others, which architecture makes sense while others do not make sense, etc. So, searching a theory for deep learning has become the holy grail in the past 5 years, holy grail of the general field of data sciences. You might ask, who cares about a theory? Why do we need it? I mean, deep learning is successful, right? So why bother? So there are several good answers for that. First, if you have a proper theory at hand, you can take this field to the next levels, and you can do amazing new things, things that we are not aware of today. Secondly, we could map the limitations of this field. We could find the parameters or features that govern the performance of whatever we do, and maybe then find ways to overcome them. And third, and don't discard this, a theory could take us from sort of black magic, which is what we have today, black magic, take us all the way to a solid scientific discipline. So these are the reasons. Now, interestingly, how many of you know this guy? This is Ali Rahimi. Ali Rahimi is a well-known researcher in machine learning and an employee of Google. Google, the mecca of deep learning. And Ali Rahimi stepped up and gave a talk in NIPS 2017. Basically, he got a prize and he gave a talk. And in his talk, he attacked deep learning. And his message was, machine learning has become alchemy. This is really a hard statement. Alchemy? A few days later, the answer came from Yann LeCun. I'm sure that all of you know Yann LeCun. Yann LeCun is the practitioner and the inventor of ConvNets. Yann LeCun gave a brilliant answer, and he said, you know what? You're right. We do need theory. We want theory. It's just that we are not waiting for it to happen. We are running like crazy. We are inventing tricks, and we are inventing methods, and we are inventing algorithms. And yes, if someone brings a theory, we'll be delighted. Okay? So he gave a lovely set of examples where knowledge, the practice, preceded the theory, such as lens and the telescope preceding optics, such as steam engine coming before the thermodynamics was known, such as airplanes flying way before anybody knew anything about aerodynamics, and so on and so forth, all the way to computers and computer science. And so even the practitioners in this field agree that a theory is missing and needed. They want it. It's just that they are not waiting for it. So how do you come up with a theory for deep learning? There are 3 legs on which deep learning is standing. 3 legs, and when you look at papers attacking the theory for deep learning, you will typically see that they attack one of those blocks, perhaps 2. So for example, when it comes to architectures, Raja Giris will tell you a lot, in fact, today in a lecture that maybe is in this hall, maybe, about architectures that we are using and their tendency to preserve distances, and why this is important for whatever we need to do with deep learning. Gita Kutinyuk and Helmut Bolsky will tell you about the capacity of those networks to cover familiar functions. Those are mathematicians trying to figure out what's going on here with these networks. When it comes to algorithms, you'll see amazing work by René Vidal, who basically tells you, don't be afraid of local minima. They are not so bad as you may think. You know, local minima are the scariest thing when it comes to the optimization of deep learning. Naftali Tishby advocates information bottleneck as the objective that we need to work on. Tami, יש פה מקום. And Stefano Soato's team did an amazing work where they shown that the stochastic gradient descent The stochastic gradient descent that all of us are using is in fact optimizing the information bottleneck. You should look at this work. You cannot read it, but it's lovely. And when it comes to data, Stéphane Mallat was one of the first to dare and say, I will bring theory for deep learning. And Stéphane Mallat attacked the issue of invariances together with his ex-student, Joan Brunner, now a professor in NYU. Rich Baraniuk and his students worked on a generative model to describe how the data is created and then motivate the architecture that we are using. In fact, our work will go very much along the lines of this one. Okay? Will be somewhat different, of course, but we are similar. If anything is similar to what we do, this is it. Roughly speaking, I would say that there are somewhere between 100 and 200 papers that qualify as attempting to say something theoretic about deep learning. 200 papers, quite a lot. So what do you think? Is there a theory for deep learning? The answer is tricky. It's not sure that I can say that there is a theory for deep learning. First of all, there is no agreement between the researchers. The languages used are very different, very hard to follow how they are connected. Interestingly, in the last fall semester at Stanford University, I'm talking about a few months ago, there was a course in the statistics department. The course was called Theories, in plural, Theories of Deep Learning. This guy here is David Donohoe. David Donohoe was the person who ran this course, a well-known mathematician. And next to him on the left is Vardhan Papian, my ex-PhD student. And the theory I will describe today basically came from Vardhan and two other students. I'll mention their names. So theories for deep learning. What they did, in fact, is to invite people to present their theory in order to see how things can merge. Interestingly, when it comes to the attempt to bring theory for deep learning, there are all sorts of flavors and all sorts of directions that are taken. Not just machine learning. In fact, machine learning is a sidekick here. You'll see people coming from signal processing and from control theory, partial differential equations. I'm bringing sparsity to this language. Stéphane Mallat will bring harmonic analysis. Everybody uses the different language. This is part of the problem of creating a unified picture. The languages are different. Ron Kimmel, my good friend, said that deep learning is just like a huge monster covered with mirrors. Everybody looking at it sees himself. And so I'm looking at deep learning and I see sparsity because this is my language. Stéphane Mallat will see wavelets and so on and so forth. David Donohoe said, you know what? Those mirrors are not just regular mirrors. They are magical mirrors. They speak to you. They tell you that you are the most beautiful. And so every one of us coming up with a theory for deep learning feels that he is the best. Okay? Today, we'll talk about the theory that we have. Yaniv Romano, Vardhan Papian, and Jeremiah Sulam, three amazing PhD students of mine that did this work. Yaniv is in Stanford now, doing his postdoc with Emmanuel Candes. Vardhan, postdoc at Stanford, doing his postdoc with David Donohoe, and Jeremiah is still searching, and we'll see where he lands very soon. Our work, remember those three legs I mentioned? Our work will go with the data, will emphasize the data. It will have some statements about the architectures. We have no claim about the algorithms. Okay, so we are not complete. And yes, definitely, we are the best. Okay? So let's dive in. My talk today will start by presenting the concept of sparse modeling of data because I'm relying on it. Then I'll show you two special cases of this model. The convolutional sparse coding, and from there, the multi-layer convolutional sparse coding. Two special cases of sparseland. And this migration will take us all the way to deep learning. Okay? So you'll see the connection to deep learning only in the last 20 minutes. So obviously, this is the main message of my talk. The secondary message is the fact that all these three, the sparseland, the CSC, and the MLCSC, all of them are generative models. You'll see what I mean by that. And generative models, they enable theory. And you'll see me doing theory. You will see me writing theorems. And if I mention this, maybe this is a good time to say that this talk is theoretically oriented. Okay? So if you are not so much into math, maybe this is not the lecture for you. And I won't be offended seriously if you just walk out. This was the fun part of the talk. Okay? אין לכם אומץ. טוב. Feel free to come to raise and go out anytime you want, okay? I'll even mark you when the point in the lecture starts where things get messy, and then you can walk out. Towards the end of my talk today, you will be familiar with multi-layered convolutional sparse modeling. So what I'm going to do now is to take this as a running title, and I'm going to parse it to words and explain one word at a time, and this way create the complete story in your heads, okay? So let's start by modeling. What do I mean by modeling? We are all processing data, all sorts of data. We are getting information from different sensors, and they are so different, so diverse, and yet they have something in common. And the common thing is the fact that all these sources are structured, each in its own way. And if you think about it really, signal processing, image processing, computer vision, machine learning are all about identifying this structure and exploiting it. This is what we do. So how do you identify the structure that exists in a source of information, in an image, in an audio? The answer is models. Let me give you an example. Here is a signal that has been measured somehow, and here is all I know about it. And this is seriously all I know. It is noisy. And I can tell you a lot about the noise. The noise is white, additive, Gaussian. The standard deviation is 1. The mean is 0. I know a lot about the noise. Please help me. This is all I know. Can you remove the noise? What do you think? Can you remove the noise? Those who think that noise can be removed are mistaken. You cannot remove the noise because taking a signal and breaking it into signal and noise means that you have to say something about the two pieces. I kept telling you about the noise. I told you nothing about the signal itself. How can you separate? Suppose that someone else comes and tells you that, hey, your signal that you are searching, I know how it behaves. It tends to be piecewise constant. You know, constant to regions of time. In that case, I can characterize my separation, my denoising, searching for the simplest piecewise constant signal that will be close to the measurements such that the residual looks like the noise I'm expecting. Many ways to formulate this. Many of them make sense. And you know what? It will work. You will get denoising. What have I done here? I have imposed a model. The piecewise constancy is a mathematical model. I imposed it on my data, and because of that, I was able to remove the noise. Now, this is something we do all the time, and not just for denoising. So what is a model? A model is a set of mathematical rules that we impose on the data, because we believe that those mathematical rules describe the structure that exists in this data. This is some sort of a belief. If you like, this is some sort of religion, because it is similar to religion in the sense that people are really religious about their choices of models. In image processing, we had a long list of models over the years. In fact, it is an evolution of models. And whenever you have a new model coming in, there is always this tension between your desire to make the model simple so that whatever you do with it will be simple. You know, I can always assume that my signal is 0. This is a lovely model. Algorithms emerging from it will be terrific. But 0 means nothing. I mean, it will kill the data. You have to be reliable to the data. And models, and people kept forgetting this, models, they are always wrong. There is no notion of exact model. And this is not a problem, because if you know the magnitude of those errors and you are working properly and you are just being careful, this is fine. I will not talk about it. So this talk is about models. החלק המתמטי עוד לא התחיל אפילו. This talk is about models because they are everywhere. They are in inverse problems. They are in compression. When you compress, you are using models. You know, when you tell me that your signal is band limited because you are about to sample it, you are imposing a model. Today's talk is about sparseland, a very specific model that we will be using, and its descendants, 2 descendants of it that I'll show you how they take us and connect us to deep learning, to convolutional neural networks. So this was modeling. Now let's talk about sparse modeling. This sparseland doesn't come out of the blue. It's relying on knowledge that has been accumulated in signal processing in the context of transforms, mostly wavelets. It is relying on elementary ideas taken from approximation theory and some tools borrowed from linear algebra and optimization. This is how this field has been created. We are even taking some concepts from machine learning, you will see where. And you know what? This model has been used, taken to applications and showing great success in long list of applications. And by the way, not just image processing. You don't have to take a photo of the screen because I'll put the slides in my webpage. Let me show you how this model finds the structure, or at least thinks it finds the structure in existing data. And I'll do that by describing patches, image patches. This is a patch of size 8 by 8. It's not just one patch. It's a group of patches, corpus of billions of patches coming from a group of images. And I'm trying to figure out where is the structure here. So the model starts by preparing a dictionary, set of patches of the same size, 8 by 8, many of them, in this case, 256. This is called the dictionary, and those patches are called the atoms. The names will be clear in a minute. And now comes the model, and the model says, here, I believe, remember those are religions, I believe that your patch, and not just this one, all of them, can be described as a linear combination of only few atoms from the dictionary. The word few here is key. You take out the word few and you kill the model. Let me have a closer look at this model. I started with a patch of size 8 by 8. 64 numbers. The first thing I did is to turn this vector into a 256 long vector. Why? Because now I have to tell you per each of the atoms how much it is involved in the mixture. So I'm looking at a representation that is redundant, 256. But this vector, it's mostly zeros. It is sparse. So only in this example, only 3 of the elements in this vector will be non-zero. So sparsity and redundancy. How much information is really kept about this patch? Only 6 numbers. Because you know what? If you tell me who are the 3 atoms involved and how much each of them contributed to the mixture, you told me everything. So what do we get? We get a lovely dimension reduction, and that's exactly what all models are about. Reducing the dimensionality, basically telling you, hey, your patch, 64 pixels? No, 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 no. 6 numbers and I tell you everything about it. This is the lovely part about models. You know, if it may appeal to you to see the following analogy. I'm thinking of our dictionary as parallel to the periodic table in the regular chemistry. In the regular chemistry, we have fundamental elements, and whenever you bring me a molecule, this molecule is a combination of those fundamental elements. And if you check, you'll see that most of those molecules, maybe all, are always compositions of only few of the fundamental elements. And just like this, our model says that those are the fundamental elements in our data, and our signals are playing the role of sort of molecules. So a parallel to regular chemistry. Here is a slightly more formal way to describe what I just told you. This machine generates signals, in our case, patches of size 64. It has a memory matrix held in memory. The matrix has 64 rows by 256 columns. In fact, every column is an atom. I'm just stretching those patches to become 64 elements long vectors. And I have 256 of them. And now, if I press on the button up there, a sparse vector alpha will be created. This vector is of length 256. It is sparse. When you multiply D by alpha, what do you get? You get linear combination of few of the atoms, exactly as I told you, and this is your signal X. And if this sounds crazy to you as a way to describe how signals are created, I completely agree. It is crazy. And this is the way I believe things are happening. Remember, models are always wrong. So, remember I told you that models should be simple? Well, this model is not simple. Let me show you how complicated it can be. Let's talk about something called the atom decomposition. I have a dictionary and it has 2,000 atoms. And now I'm taking 15 of them that I choose arbitrarily, and I'm mixing them and creating a signal. I'm creating a signal, and now I'm asking you, here is the signal, here's the dictionary, now figure out who are the atoms that I used. What do you have to do? You have to go through all the possibilities of choosing 15 out of the 2,000. This is the number. If every one of those tests will take you 1 nanosecond, you are looking at billions and billions of years to conclude this search for those 15 atoms, such a simple problem. So it looks like we're stuck, are we? Let's pose again this question to describe the very same problem in a slightly more formal way. What I just told you is that we have the dictionary D, a matrix. I just gave it to you. You have the signal X, and I'm asking you to solve for alpha. So this is a linear system of equations. The problem is it's underdetermined, more unknowns than equations. But you know that you are searching for a sparse alpha, so you will be solving this. L0 norm here is counting the number of non-zeros in the vector alpha. And so what I'm trying to do here is to search the sparsest alpha that explains X. Sometimes you don't get X. You get a noisy version of it. Why? So you will be searching for an epsilon-closed explanation to Y, an alpha that will be sparse such that d alpha is up to epsilon away from Y. The problem is, those two problems are NP-hard. You cannot solve them. So what do? You approximate. You go to approximate. You can use relaxation methods such as basis pursuit, or greedy methods such as thresholding or OMP. Let's have one slide on them just to illustrate what I'm talking about. Basis pursuit is so simple. It basically says, you are searching the sparsest alpha. L0 is so nasty, let's replace it with L1. That's it. L1. Chen, Donoho, Saunders, the year is 95. They write a paper and they say, you know, when we replaced L0 with L1, it works in the sense that we get a sparse solution and it is close to the ideal one that we wanted so much. So this is great. Matching pursuit is a greedy algorithm. It basically builds this vector alpha one element at a time. It starts with an empty vector, and then it sweeps through all the vectors as atoms and asks who is the atom that is doing the best job in bringing the two sides of the equation. And once you find it, you stick with it, and you search the second atom, who wants to join, etc., etc. Thresholding, and please remember my word now, thresholding is the dumbest thing you can do. Thresholding is basically a matched filter. You take your signal Y, and you do inner product with all the atoms. This is the essence of D transpose times Y. And then, when you have this inner product, you simply kill the small values. Those that are near 0 are null to 0, and the rest are left intact. This is the thresholding algorithm. And that's it. 3 pursuit algorithms. Are they working? Let me show you an example. This is the example I just given you. 2,000 atoms, out of which 15 were turned on. These are the red points. So for example, I don't know if you see that, but if this red point is here, it means that the index 1850 has a coefficient minus 1.5 or something. Now I'm using basis pursuit, simply L1. You can solve this using MATLAB in no time, not those billion years definitely. Here is the solution. Terrific solution. Best. Ideal. Is it a coincidence? No. And this is bringing me to talk about the amazing part about Sparseland, the theory that has developed in this field, basically providing guarantees of success under some conditions. The message is, you have a pursuit algorithm, it is an approximation, but sometimes you can trust it. It does excellent work. Let me give you a flavor of those theorems by showing you just one of them, one representative that I will be using later on. But in order to do that, I need to define something called the mutual coherence. So let's talk about that. Mutual coherence is simply a measure of goodness of the dictionary, a proxy for how the dictionary is good. So I'm taking my dictionary D, and I'm assuming that the columns have been L2 normalized, and I'm multiplying D transpose by D. This is a Gram matrix. And of course, since those columns are normalized, then the main diagonal are all ones, and the coherence is the maximal absolute value in the off diagonals. The smaller it is, the better it is. Okay? This is mu of D, a scalar, a number, 0.1. All the results I'll show you today are relying on this coherence. Those of you who are familiar with Sparseland may have heard of RIP, ERC, Spark. I will not talk about them. There are many other ways of quantifying the dictionary goodness. Okay, and now armed with this, let me show you this theorem. And the theorem goes like this. Here is this machine generating a signal X by taking a sparse vector and multiplying it by the dictionary. Now, you don't get to see X. This is too easy. Let's add noise to it. I'm adding noise, and the noise has bounded energy. This is all I know about it. And I'm getting a signal Y. Now I'm trying to figure out who are the atoms that created Y. So I'm trying to solve this. I'm trying to solve for the sparsest alpha to explain Y up to an epsilon error. But I told you, I cannot solve this. It's impossible. So what do? I go to L1. I go to L1, and I'm getting some sort of estimate. Another question is, how far is this alpha hat from the alpha I wanted to get? So here is a theorem. And the theorem says, you know what? If this alpha here was sparse enough to begin with, trust me, basis pursuit is going to do very well. In what sense? In the sense that alpha hat is not going to be far from the true alpha. Here is a bound on how far they are. Okay? Now, this is a typical theorem. We'll see several of them today. Notice that some text is highlighted. This is the only part that you need to read. The part that is grayish, not to be read. Okay? Just for completeness. Few comments about this theorem. First, observe that if there is no noise, if epsilon is 0, this bound here is 0. What does it mean? It means that alpha hat equals alpha. So in this case, the basis pursuit finds exactly the solution. Not approximately, exactly, if alpha was sparse enough. Second comment has to do with the fact that this theorem is worst case. Much better and more optimistic claims can be made. I simply didn't go there. Okay? And third, this is just one typical example. There are many such theorems for many other pursuit algorithms. In fact, even the thresholding algorithm, this dumb method, even that has some guarantees for success. Of course, harsher conditions, but guarantees for success. We were counting difficulties with Sparseland. Here is a second difficulty. You know, I'm working with face images. Someone else is working with audio. A third person is working with, I don't know, predicting the market. Everybody needs his own dictionary. What do we do about it? We learn. This is where we imitate things for machine learning. We basically take a lot of signal examples from your source, and we try to figure out who is this dictionary that sparsify them. We are searching D out of signal examples. There are many such algorithms. I will not talk about it today, but it will accompany us. And if we are discussing difficulties, here is the prime difficulty. Why should you trust this model? It's so crazy to believe that signals are created of atoms. So how do you answer that? There are two lines of answers. One of them is saying, you know what, let me show you a connection between this model and existing models that make sense to you, like GMM, etc. And then you'll see that this model is actually quite smart. Another option is to say, hey, we tried. We simply plugged it into applications, and it works great. And we have both these answers. So the bottom line is, there are some difficulties, but there are some constructive answers. And this model is safe and can be used. And we have been using it quite a lot in the past, say, 10 years. This field is rapidly growing with a lot of activity, and there is a bunch of books that were written on this field. I published my book in 2010. This is it. You should buy it. It's a terrific book. Here are some books that were published afterwards, all of them under the title of sparsity. All of them. Would you believe that? There is a MOOC. There is a course under edX if you are interested in this field. If you are interested, just go. It's free. You can you can enter and see the lectures, etc. Okay. Now I'm finishing this part by mentioning how we practice Sparseland in image processing. When it comes to images, you cannot train a dictionary, just too big. And so what do? You break the image into patches. You break the image into patches, fully overlapped patches. You impose your model on those patches. You work on the patches and then merge them back in order to create the solution. This is the common practice, and it works fine. So what is the meaning of this? The meaning is, rather than telling you what is the model for this image, I'm telling you how its patches are expected to behave. And what am I telling you? I'm telling you that every patch in this image is expected to have a sparse representation with respect to the same dictionary. This is the language that is used here. For years, this troubled us, and we kept searching for ways to explain to ourselves what's going on, and this brought us eventually, 3 years ago, to the convolutional sparse coding model, which is what I'm going to talk about next. So remember, again, there is a model here that says every patch in the image is believed to have a sparse representation under the same dictionary. This is the part where things start to get more complicated. If you want to leave now, no problem. Sparse, or convolutional sparse modeling. This is the model. This is a model that describes how sorry. The work from now on is the work by Yaniv, Vardan, and Jeremiah, and it was published in a series of papers in the past 2 years. And now, this is the model. Okay? Some of you may have seen it because it appeared in many papers, especially by Jan LeCun. Jan LeCun advocated this model since mid-2000s until recently because this model sort of connects lovely to CNNs. Okay, so what is this model saying? It says the following. This is your image X, and it is basically believed to be the sum of convolutions. Okay? What kind of convolutions? Filters, local filters. You can think of this as 7 by 7, for example. How many such filters? In this case, 16. So M in general, M filters. And every one of those filters is convolved with a sparse matrix of the same size as the image. So in another language, basically, you are taking every one of those points and replace it with the filter that it belongs to, and then you just pile filters with different scales, and you create your content image. This is the model. Here is another way of looking at it, a more pleasant way in my view. And this is a matrix form. And it says the following. Your signal X, now I will think of it as a long vector. And from now on, I think of signals as 1D, not to be messed with 2D and 3D images, but everything can grow to these dimensions. So my vector X is believed to be sum of multiplications of matrices Ci, those are the Ci's, convolutional matrices, circulant and bended, circulant because of the convolution, and bended because the filter is of small support. And those Ci are multiplying vectors, gamma I, that are simply those maps that we saw before, stretched to become one long vector. And now, if we can write this, you can take all the Ci's and put them one next to the other, C1, C2, up to Cm, and this horizontal stretch of matrices is multiplying a one long vector, sparse vector, gamma 1, gamma 2, all the way to gamma m. Okay? So what do we see here? We see a dictionary D multiplying a sparse vector gamma. So obviously, yes, this is a special case of sparseland. Special case in what sense? In the sense that the dictionary has a structure. It cannot be anything it wants. It is actually built as an amalgam of circulant matrices, banded circulant matrices. Okay. Here is the dictionary. In the case of 3 convolutions, we typically like to look at it a little bit different by taking the first atoms of all the 3, putting them together, then the seconds, thirds, etc., and we get this block structure where every one of those blocks is the same thing. Okay? Simply you shift 1 and go down 1, and you create this block structure. It's the same thing. Simply a permutation of the columns. Okay? This is the dictionary we work with. Now, why are we fascinated about this model? Why is it connected to what I told you before? Because of the following thing. Here is the general belief on our signal X. X is D times gamma, where D looks like this. Remember, this is a global model. X is the global signal. Now let's have a look at a patch of it. Let's take a patch in location I. Rix goes to location I, cuts out a patch. This patch equals all this stripe multiplying gamma. But this stripe is mostly zeros. In fact, this is the only active part, right? This is the part that does the work. All the rest are just multiplying by 0. And this part is multiplying what? A portion of gamma. Let's call it gamma I. So we have a stripe dictionary multiplying a stripe vector. And so I can tell you that Rix, the patch, is omega, this omega, multiplying this portion of the vector that we just called gamma I. Okay, now let's move one sample down. Fully overlapped patches, one sample down. I'm going one down. I have to move m elements to the right. And who do I meet? Omega, all over again. This is exactly the same omega. And this omega now multiplies gamma I plus 1, okay? Which is m elements shifted down portion of the vector. And so I can write that Ri plus 1x, the patch, the next patch with the overlap to this, is omega times gamma I plus 1. What am I showing you here? I'm showing you that this model believes that every patch has a sparse representation with respect to the same dictionary. CSC is the proper way to go when you want to say something global about your signals, but want to think in terms of patches. This is the language that we have been using without really noticing. So we are trying to make some order here. This is why we are so fascinated about this model. one of the first things we did when we started working with the CSE is to search whether the theory we have in sparse length applies to this model. Let's try. Remember, I'm trying to figure out who is the sparsest gamma to explain y up to an epsilon error. And I just shown you a theorem. And the theorem says basis pursuit is going to do well if you just satisfy this condition. So let's look at this condition. What is mu in our case? So it turns out that if you take only 2 filters, m equals 2, and those filters are of 64 elements long, then the best coherence you could ever get, and this is something that can be proven, is this number. And if you plug it back into the bound, you get that I'm allowing you to have 4 non-zeros in the entire vector gamma. 4 non-zeros? You want to create the complete image from 4 filters, copy it somewhere? Impossible. So clearly the theorem that we have is meaningless. It cannot guarantee anything. We don't have a theory. So what do? We started searching for a new theory. And what we did is to turn to discuss local sparsities instead of global sparsity. Rather than talking about how many non-zeros exist in the entire vector gamma, we are now searching for the number of non-zeros in stripes. This is gamma I, this is gamma I plus 1. They are shifted by m elements each time. And now what I'll do, I'll go and sweep all over and search for the gamma I that is mostly populated. So for example, if it is 5, it means that I found a piece that have 5 non-zeros, and all the rest have no more than 5. Okay? Let's talk about this as L0 infinity. L0 infinity is just our way notation to tell you exactly what I just said. Finding the stripe that is mostly populated. Now, from now on, rather than searching for the sparsest gamma globally, let's search for the sparsest gamma locally. Find the gamma that this measure of it is the smallest. Now, if you think about it, it makes a lot of sense. Why? Because if this value is small, what does it mean? It means that every one of those gammas, gamma I, gamma 1, gamma 2, gamma 3, all the way to gamma last, all of them will be sparse. And that's exactly saying every patch has a sparse representation with respect to the same dictionary. Those are the representation of the patches. So it's the language we need. The question is, can we generalize the theory that we are so familiar with, 10 years of massive work in sparse length, developed a theory, can we take this and migrate it to the new notion of sparsity? The answer is yes. We have done it. There is a paper, in fact, 2 papers on this. I will give you just a glimpse of one such result. Here is the glimpse. It basically says the following. You want to solve this. This is horrible. This is NP hard. Replace with L1, just like we did before. Now, this L1 is crazy because it doesn't even know that I'm searching for local sparsity. But I will use L1 nevertheless. I'm using it, and here is a theorem that says, you know what? If your gamma that created your signal is sparse enough locally, then I guarantee you that good things will happen. Basis pursuit will actually perform well. In what sense? It will identify the dominant elements, it will have a unique solution, etc., etc. So we have this result, and now why are we excited about it? Because, you see, this number here, it could be 4. But this 4 is not 4 non-zeros for the entire vector gamma. It is 4 per each stripe. The entire vector gamma may have order of n, capital N, non-zeros. So now the theorem covers really massive images with a lot of content. And now, I just finished talking about the convolutional sparse coding, and all I need you to take from what I've just shown you is that there is a notion of local sparsity, and it replaces global sparsity, and that there is a theory that supports statements that pursuit algorithms are successful in treating it. You can forget all the rest. And now we are getting to multi-layered convolutional sparse modeling. I still believe in CSE. My signal is still believed to be a multiplication of a dictionary that is a bunch of convolutions times a sparse vector. But now this will be D1 times gamma 1. Why? Because obviously there is a D2 and gamma 2 coming in a minute, in a second, in fact. Here they are. In fact, what I'm telling you is that gamma 1 itself is not just sparse. It is sparse, and on top of that, it has to obey some structure. It is by itself the multiplication of a set of convolutions multiplying a sparse vector gamma 2. So this is D2, and this is gamma 2. And this model is the multi-layer CSE. Okay? So the multi-layer CSE is basically a CSE model, because this is still true, But on top of this, we add additional constraints on gamma 1. It cannot be anything it wants. And by the way, if you are troubled about this M1 here, you can ask me later. It's not issue, it's just because of the tensor structure of the filter that we are using. Okay, so this is the multi-layer CSE, and obviously not just 2 steps, you can take it K steps in general. Now, let me give you a little bit of intuition about this model. This slide is perhaps the most important one. Our signal, X, is a linear combination of atoms from the dictionary. See, these are atoms, and we are combining them linearly to create a signal. True, this is still true. But now, I'm adding another piece to the story. I'm telling you that this gamma 1 is in fact D2 gamma 2. And so, basically, D1 times D2 times gamma 2 is also X. Or you know what, if you have K layers, you can say that there is an effective dictionary, D1, D2, all the way to dk, and your X is D effective times gamma K. So looking at this only, what do you see? You see a Sparseland model, a dictionary multiplying a sparse vector. This is why I told you in the beginning that this model is a special case of Sparseland. Special case because of the structure of D effective, and that's it. But in fact, the dictionary D effective has a structure of convolutions. So in fact, it is a special case of CSE. But now comes the twist. This is not our model. This is just part of the story, because this equation itself doesn't reveal the fact that we demand gamma k minus 1 to be sparse, gamma k minus 2 to be sparse, all the way to gamma 1. All of them are forced to be sparse. So this is the key difference. And my way of explaining this is perhaps the following. Look at me. I am built of atoms. You can describe my body as being built of atoms. But you could describe the very same body as built of molecules. You could describe the very same body as built of cells, of tissue parts, of body parts. There are many scales and many ways to describe the very same signal, the very same thing. The same thing happened here. Let me show you why. You see, when I told you that X equals D times gamma 1, I'm telling you that the signal is built of atoms. But when I'm telling you that X equals D1, D2, gamma 2, who are now the atoms? The atoms are the multiplication D1, D2. Let's have a look at the first column of this matrix. The first column is all D1 multiplying the first column of D2. When you take the whole matrix D1, multiplying by the first column of D2, you are combining few atoms. What are you creating? A molecule. So the superatoms in D1, D2 are sort of molecules. And my signal now is believed to be built of molecules as well. And so we build signals from atoms, molecules, cells, etc., going up the scale, and all of them are forced in parallel together. This is why this model is much stronger than the regular sparsity. And if all this doesn't make sense to you, let me give you an example. Here are the dictionaries that we have learned for the MNIST database. What you see here is group of filters for D1. You don't see the atoms. I'm showing you the filters creating the atoms. So these are the filters, and what do you see? You see edges, edge detections of all sorts. You can create your digits in MNIST using a few hundreds of those, okay? Terrific. Here is D1 times D2. I cannot show you D2. It's boring. You cannot look at it. But I can show you D1 times D2. What do you see here now? You see all sorts of elongated curves. You can create the very same digits using a few dozens of these atoms. And here is D1 times D2 times D3. And now the atoms are nearly complete digits. And now you can create your digit using few of those atoms. And we'll see this example coming up later on. Okay, so we have just come up with a definition of a model, the multi-layer convolutional sparse coding. And now let's talk about the pursuit problem. Remember, what is the pursuit? Given the signal, find the representation, find how it is built. You give me the signal that is believed to obey those equations. Observe, X is believed to be D1 times gamma 1 when gamma 1 is locally sparse, and so on all the way down to K. And now you give me X, and of course you have to give me the dictionaries as well. And if you do that, I'm supposed to give you the gammas. This is the mission of a pursuit algorithm. Just like in the single-layer model, in the multi-layer model, we need to find all the gamma i's. And again, you never get X. You never get a clean signal that is perfectly in the model. You get a signal Y that is epsilon away from this, and you're searching for the explanation of it that will most make sense to you. Okay? You're searching for a set of gammas, gamma 1, gamma 2, gamma 3, all the way to gamma k, that will be locally sparse and could explain your signal. We would like to solve this problem. Let me show you how it is actually solved for the MNIST database. This is the given signal y, and now this is gamma 1 that was found. And it was found such that if you take gamma 1 and multiply it by d1, you get this signal x. Now, the very same signal x can be created by taking gamma 2 and multiplying it by d1, d2. Now observe, here we need the 213. Here we need only 30 non-zeros to create the very same signal. Why? Because those are molecules. These are atoms. And in this language, going to gamma 3, you need only 5 elements to combine together to create your signal. And what I'm telling you in this model is that all 3 are required in parallel. They are not just one of them is working and the other are resting aside. No, all of them are forced. And this is why this model is so strong. So we are about to design a pursuit algorithm. Now, I remind you, among all the possibilities we have to design a pursuit algorithm, what is the dumbest way? Thresholding. So let's go for thresholding. Thresholding, I remind you, works like this. You have a dictionary multiplying a sparse vector, and there is some sort of disturbance. You want to find this gamma. What do? You do inner product between the signal and the atoms, d transpose time y, and threshold. Now, how do you threshold? I've shown you before the hard thresholding. This is the blue line. But in fact, there is also an option for red line. This is soft thresholding. It has some justification. And you know what? You might even want to consider the green option. The green option comes up when you believe that your model parameters are non-negative. Okay, now armed with this knowledge, let's go and invent a pursuit algorithm. The dumbest thing we could ever think of. So here is my problem. And what I'll do now is to work layer-wise. I'll start with the first layer. Y minus d1, gamma 1 needs to be close up to epsilon with the gamma 1 that should be sparse. Here is my algorithm. Take y, multiply by d1, transpose, and threshold. If you do that, you get an estimate of gamma 1. Now, look, one equation below. This is an estimate of gamma 1. Now, from it, I can create the estimate of gamma 2. How? By multiplying d2, transpose, and thresholding again. What is this? This is a feed-forward neural network. This is a feed-forward convolutional neural network. Okay? So what am I telling you? I'm telling you that whenever you are running a feed-forward convolutional neural network, you are essentially running a pursuit algorithm, the dumbest pursuit algorithm, okay? For what? For signals that are believed to come from this model that we have shown, okay? And if you are troubled by let me say something about the ReLU. ReLU is a threshold that needs a bias. The same thing happened with the thresholding we have. This is a complete analogy, okay? Terrific, but this is not the message. This is really not the message of what I'm trying to convey here. Here is the message. We have a machine, and we believe that we know how it works. We believe that we know how signals are created from it. We believe that those equations are the reason for those signals to be created, okay? Now you get a signal X, you have a noisy version of it. You plug it into a machine, an algorithm, that tries to figure out who are the representations, and you have all sorts of options. For example, the layered thresholding that I've shown you, or maybe some other algorithm. Maybe later we'll invent something. But now I can do something that we could never do before. I can ask questions, such as, under what conditions on the sparsities here, this block will be successful? Successful in what sense? And all sorts of these questions. So here is the theory. This is exactly where the theory steps in. Why? Because this is a generative model. It is a model that describes how a signal is created, and therefore I can analyze performance. This is a key issue here. So just to show you that this can be done, let me show you a theorem that we have developed, one among few that we have. And the theorem says the following. The algorithm I've just shown you, the dumb algorithm that basically leads to feed-forward neural network, it is actually guaranteed to succeed. If all the gamma i's are locally sparse, okay, obeying the model in some sense, and this horrible expression explains how sparse they should be, then I guarantee you that the layered thresholding using hard thresholding is guaranteed to find exactly the location of the non-zeros. This is a terrific outcome, okay? Based on local sparsity of the representation and some properties of the dictionary, observe that the coherence is always in our equations, mu of. We are guaranteeing success of an architecture that is working for us in deep learning, this feed-forward neural network. On the downside. On the downside, we have the issue of contrast. Look at the ratio there that is highlighted. We are sensitive to the ratio between the smallest and the largest values in the non-zeros. And if this ratio is too big, we are dead. And this is not an artifact of the proof. This is an artifact of the thresholding, okay? And it has to do with some work that you have seen about how you can cheat networks to change their labels based on slight additive noise. I'm sure you have seen this. It's related to this. The second problem is error growth. This formula at the bottom line shows that as you go deeper into the network, your error propagates and grows. This is nasty. This is not something you want to show. And third, even if you don't have noise in your signal, if this epsilon L0 is 0, you will get errors. Thresholding will never give you perfect recovery. So can we do something about it? Of course we can. This is just the dumbest pursuit algorithm. Let's come up with a slightly better one. Let's come up with layered basis pursuit. Very similar, but replace the thresholding, which is so crude, with something that is more elegant, basis pursuit. You solve basis pursuit given y and find gamma 1. You have an estimate of it. You plug it in and estimate gamma 2 and go on this way. Amazingly, this was invented in 2010 under the name Deconvolutional Networks by Zahler and his co-authors. So this is a horrible competition that we have with the practitioners. They invented so many things, it will take us years to come up with things that they have not seen. But we will get there. Layered basis pursuit. I'm finishing in 2 minutes. Here's a theorem about the layered basis pursuit. It basically says that if all those gammas are sparse enough to begin with, then I guarantee you that basis pursuit performs well. This is terrific. Now observe that we are no longer sensitive to the contrast. And if there is no noise, observe that the error, where is it? Here. The error here is multiplying this value. If this is 0, all the errors are 0. Basis pursuit in chain will do perfect work. So this is much better. Why is it not used? In fact, it is used. Let me show you how it is used. Think about the following scenario. I have a model that has 10 layers. My model has 10 layers. Every one of those layers requires you to solve a basis pursuit. So you have an outer loop that requires solving 10 basis pursuits. Now, how do you do that? You use an algorithm called iterative soft thresholding. Iterative soft thresholding is an algorithm that works like this. This operator over there is simply a thresholding, a ReLU in our language, okay? And you just multiply by the filters and the filter transpose, and that's it. And what do? You do, say, 50 iterations of them. So you do 50 iterations of this, 50 iterations of this per each basis pursuit, but you have 10 of them. So you have 50 iterations and 50 iterations 10 times. Unfold it, and what do you get? You get a feed-forward neural network with some jumps, looking very much like ResNet, very much, but now the depth is 500. You have a very deep network. But what is it? Just 10 basis pursuit, that's it. This is explaining, in retrospect, why networks are so deep. Because the model is deep, and because you need a bunch of iterations to treat every one of those layers. In fact, in our language, every one of those 50 iterations will require the same set of parameters. And in the sake of saving time, I have a button here. Time to conclude. So what have we seen today? We have seen that there is a need for models, and we spoke about sparseland as a specific model. We have seen how we can take it to the special case of convolutional sparse coding, for which we developed a new theory. Then we moved to the multi-layer model, and in the multi-layer model, we saw a lovely connection to CNNs. And there are, again, 2 take-home messages. The first one is, all these 3, sparseland, CNN, CSC, and multi-layer CSC, they are all generative models, and therefore they enable us to come up with theory that we have never seen before in deep learning. Second message, obviously, the connection to neural networks. We believe that there is some sort of foundation here to build a lovely theory for deep networks, coming up with new architectures, etc. That's my talk. Thank you very much. I'm sorry that I took too long.
Thank you. Thank you, Mickey. And we have a few minutes for questions. And as you raise your hand, I'll want to ask one question about learning. And
Yes.
how do you're talking about neural networks? What's about the learning?
I don't know if you noticed, but in my talk, I never used the word labels. Never. Where are the labels? Where is the learning? So you can have two ways of looking at it. One way is to say, forget about labels. I'm not interested in recognition or classification. I'm thinking unsupervised learning. I'm trying to figure out the structure that exists in signals. And then I'll just work the way I just shown you. Another option, and this is an option that appears in a paper that we have just released to archive, is to say, no. There are labels. Remember this machine that generates signals? Whenever it generates a signal, it generates a label from it. And the label is simply a linear combination of the coefficients of those gammas. So you know the gammas, you know the label. And so everything I've done today in an attempt to recover the gammas is about basically finding the label, because if you know the gammas, you know the labels. Now, regarding the learning, we need dictionary learning. In the SparseNet model, we rely on dictionary learning. There is just one dictionary. In the CSC, we need dictionary learning. We are learning filters. We have such algorithms. In the MLCSC, we need dictionary learning. As of today, there is only one algorithm that knows how to do it. It's not a good algorithm, but it is the only one, the one that we released half a year ago to archive. And I'm sure we will see a bunch of such algorithms emerging later on. Dictionary learning for the multi-layer CSC is nothing but deep learning, okay? The part of learning in deep learning. So this is the learning. It is very much missing in our work, and I'm not sure we could close this gap. I'm not sure we could come up with theorems that will tell you that your learning is guaranteed to succeed. This is a challenge. Maybe one more question?
I think you just, I wanted to ask about how you learn the DI.
So what
Because
we
you
did,
said, given we have DI, but
right.
how do you get it?
So again, this algorithm that we have, and you saw the results of it, by the way. The result in MNIST came from this algorithm. What we did is to say, oh, it's too complicated to force the gamma i's to be sparse. Instead, let's replace that and force the dictionaries themselves to be sparse. Because if a sparse matrix multiplies a sparse vector, the outcome is a sparse vector. Okay, does it make sense to you? It should. So a sparse matrix multiplying a sparse vector creates sparsity in the representation. So we force sparsity on the DIs and we learn them. And this is how we got the filters that you saw. Is this a good algorithm? No. We don't feel comfortable with it. But we needed something to start with. And as I told someone here before, when you have a bad algorithm, this is a terrific paper because it will be cited a lot. Thank you very much.